Hello everyone. Uh, Today we will talk about trees and graphs in this session. Previously you have learned about things like linear data structures like arrays, linked list, and all. But today we will learn about a hierarchical data structure. Okay, so it's not a linear data structure anymore; it's a hierarchical data structure, which means that some nodes comes below the other ones, means it depends on its parent nodes. Okay, so some elements in the data structure depends on the other elements on the means some elements in the data structure depends on others. So that's what a hierarchical data structure means. So for better understanding, let me present my screen first. So basically, if we talk about trees and graphs, so as I told that it's a hierarchical data structure. So if you see an image, so you see that it's similar to a real life tree, just it's the opposite of a real life tree. So the real life tree expands as it goes up, right? But in data structures, trees and graphs expand as it goes down. So the first node, that is one here, is generally called the root node. Okay, so 2 and 3 are the children of 1. So as you can notice here that 2 and 3 are the child or children of 1, so they depend on the node 1, right? So that's what I was trying to tell, that when that some elements in the data structure depends on other elements. So here you can see that 1 is the root node, so 2 is the child of 1 and 3 is another child of 1. Similarly, 4 and 5 is the other children of 2, 6 and 7 are the children of 3, 8 9 are the children of 4, 10 and 11 are the children of 5, 6 has a single child, that is 13, 7 has a single child, that is 14. Okay, so this is a basic overview of what trees are. Okay, so now you might be wondering that what are the real life applications of trees, right? So let me give you some real life applications of trees. Okay, so everyone of you has used files, right? Files or folders in your computer. Okay, so files and folders are generally managed by a tree data structure. Okay, so you go to the root directory. First you go to your user or the root directory, which is usually your name. So let's say if the name of your PC or the name of your MacBook is, let's say, user 1. Okay, so the root directory is user 1. Okay, so inside that user 1 folder there are plenty of folders. Okay, so the root directory is the parent in this case, and the immediate folders are the children of the root directory. So when you open the root directory or of your Mac or of your PC, you get a bunch of folders. So let's say there are two folders in your root directory of your Mac or PC. Okay, so let's say inside folder 1 you have another two folders. So let's say inside folder 1 you have folder 3 and folder 4. Okay, and then again let's say inside folder 3 you have two files. Okay, file 1, file 2. So you can now imagine that file system or file explorer are generally controlled by a tree system, that inside root directory there are two folders, inside folder 1 again there are two folders, and inside, let's say, folder 3 there are some files or again some folders. So these are the means this is a real life application of a tree. Okay, so if I talk about a real life application of a graph, so let's say you want to go from your home to your friend's house. Okay, and there are plenty of paths through which you can go. Okay, so let's say there is a path 1, there is a path 2, there are other ways of going to a friend's home also. So basically there are plenty of ways of going home, so you need to find the shortest path, let's say. So this can be solved by a graph. Okay, so finding ways to go to your friend's house and finding the shortest way to go to your friend's house are the real life applications of graphs. Okay, so let me first of all let me get means explain some of the basic terminologies of a graph. So if you see the image here, so if you see one, so every thing, that means every 1, 2, 3, 4, 5, these are called nodes. Okay, so uh, in simple words, node you can denote as a place. Okay, so let's say you are trying to go from your friend's house to your house, or let's say you are trying to go from your house to your friend's house. So your house is a node, your friend's house is a node. Okay, so similarly, every every object or every endpoint of a edge. Okay, so every endpoint of an edge is generally called a node. Now what is an edge? So edge is the line or the connection between two nodes. Okay, so when you have two nodes and some line or some connection joins those two nodes, those are called edges. Okay, so so the first means the topmost node is called the root, and the bottommost node which doesn't have any children, for example 8 doesn't have any more children. Okay, so the nodes which doesn't have any more children are called leaves. Okay, so similarly in real life also, like leaves are the endpoints of a tree, means you don't go after leaves, like leaves are the endpoints of a real life tree also. So 8 here is a endpoint, means after 8 you can't go anywhere down, so 8 is a leaf. Similarly 9, 10, 11, 13, 14 are also leaves. Okay, so I understand, I hope that everyone understands what is a root, what is a leaf in a tree. Okay, so basically if I talk about the next thing, that is the basic algorithms of a tree and a graph. So those are BFS and DFS. Okay, so let's say you are given a graph. Okay, so means let's say you are given a tree for simplicity. So you are given this tree. Now you want to explore this tree first of all, right? So you want to explore that from one, where we can go. So from one you can go to two or three. From two you can go to four and five. From three you can go to six and seven. Okay, so and so on. So you need some algorithm or some technique to explore the tree. So now there are two such algorithms. Let's say the first one is DFS and the second one is BFS. Okay, so DFS is depth first search, and BFS is breadth first search. Okay, by the names I think some of you can guess that how things will work. So let's take this simple tree. Let's say 1 2 means 1 has 2 children, 2 and 3, 2 has 2 children, 4 and 5, 3 has again 2 children, 6 and 7. Okay, so in DFS or in depth first search, we start from the root node. Okay, so we start from 1 and then we take one of its children. So let's say we take 2. So we go to 2. Okay, so again from 2 we go to its another children. Okay, so let's say we go to 4. From 4, since 4 doesn't have any more children, we come back to its parent. Okay, so we come back from 4 to 2. So after coming back to 2, we check that whether any more children is left or not. So we have explored 4, and like we are yet to explore 5. Okay, so we next explore 5, and from 5 we again go back to 2. So now both of the children of 2 are explored, 4 and 5. So from 2 we go back again to 1. Okay, so now we come back to 3s because 3 is not explored. Okay, so we have explored 2, but one of the child of 1, that is 3, hasn't been visited or hasn't been explored till now. Okay, so we now go to 3. From 3 we select one of his children, that is 6. From 6 we again come back to 3 because 6 doesn't have any children. So now 3 has one child which is not yet visited, that is 7. So we visit 7. So from 7 we go back to 3. So now all the children of 3 are visited. So from 3 we again go back to 1, and we have traversed the whole tree basically. So first we have gone from 1 to 2, then 2 to 4, then we came back to 2, and from 2 we went to 5, then we went back to 1, and then we explored 3, then we explored 6, and then we explored 7. So this is basically the procedure of depth first search. And the reason why this is called DFS, because we go on exploring deep. Means we go on exploring in, means we keep on increasing the levels till we exhaust. Here you can see that we went from, we first started with 1, then we went to 2, then we went to 4, and we stopped there because we didn't have any other place to go, because there are no more children of 4. Okay, so if 4 had a children, we would have gone to a children of 4. Okay, so basically we keep on going deep as we can in depth first search. So we only backtrack, or we only retrieve back only when we don't have any other option of going deep. Okay, so that's why it's called depth first search, because like we keep on going as much deep as we can. Now if we talk about breadth first search, here instead of going deep, we first explore all the nodes of a particular level. Okay, so what is a level? So level is basically the depth of a node. So node 1 has a depth of 0. Okay, because it is at the topmost level, and everything in computer science starts with 0. Okay, so it is at the topmost level, so node 1 has a level of 0. Nodes 2 and 3 has a level of 1. 4, 5, 6, 7 has a level of 2. Okay, so in breadth first search, we first explore all the nodes of level 0, then we explore all the nodes of level 1, and then we explore all the nodes of level 2. Okay, so I guess now you can identify that how BFS will work. So let's make a dry run of how BFS will work. So first we will traverse all the nodes of level 0, that is 1. There are no more nodes of level 0. Then we will traverse all the nodes of level 1. So we will explore 2, and then we will explore 3. Then we will go to level 2. That is the last level. So we will explore 4, 5, 6, and 7. Okay, so this is a basic BFS traversal. uh, there is a question that what if they are saying starting node must be 2 in DFS? Yeah, that's perfectly fine. You can start in node 2 also. In that case, like the tree will look different. Okay, so if you want to start from 2, okay, so the tree will look something like this. Like the root node will now be 2. Okay, and the children of 2 are 1 and 5 here, if you can see. So the two children will be 1 and 5. Okay, now 1 has 3, 6, and 7. So 1 will have 3 here, and 3 again has 2 children. So that's 5. 3 has 6 and 7. So this is 6, and this is 7. Okay. Similarly, 2 again has another child, that is 4. Okay, so in this case 2 has 3 children. Okay, so and 5 doesn't have anything. Okay, so the tree will look like this if you start from the root 2. Okay, so 2 has 3 children, 1, 5, and 4. Similarly, 1 has a single child in this case, that is 3, and 3 has 2 children as before, like 6 and 7. So this is called rerouting of the tree. Like if you want to start from 2, the tree will be modified like this. Means you need to visualize the tree like this. Okay, so this is the thing when you want to uh, start from 2. So this is basically the basics of DFS and BFS. So in DFS you can start from any node. Okay, so it's not compulsory that you have to start from 1 here only. As I told just before, that you can start from 2 also, just the structure of the tree will change accordingly. Okay, so if you start from 2, so the sequence will change. Like this is the sequence if we start from 1. So if we start from 2, the sequence of both the DFS and BFS will change accordingly as I explain the algorithm like this. Okay, so now let us see some of the means how would you code DFS and BFS uh, to get this. Okay, so now DFS uses LIFO structure. Okay, so last in, first out. So basically, when you put an element, so basically DFS uses stack. Okay, so initially the stack is empty. Initially the stack is empty, and you put the parent or the root node in the stack. Okay, so initially the stack will have the root node. Okay, and we all know that in stack the last element is taken out. Okay, so that's why it's called LIFO, last in first out. So the last element will be taken out. So every time we take the last element of the stack unless the stack is empty. So while the stack means while the stack is not empty, we take out the last element of the stack. So let's say we say this node as current node. Okay, so this is we take out the last element of the stack, and we push the children of this element in the stack. So if the last element is the root, so now we will push the children of the root into the stack. Okay, so what we will do, we will loop over all the children of the current node. So we will loop over the children of the current node. Okay, and we will push them in the stack. So we will push them in the stack. Okay, and this is enough. Like this will give you the DFS sequence. Okay, so you start with stack, means you push the root node, the node you are willing to start with, means that will be your first node. So you push that, and every time you take the last element of the stack, and you push the children of the current node into the stack. Okay, so like this you will be able to traverse the tree. Okay, so what we did when we did manually, we first pushed one, and then we checked for the children of one. Okay, so we checked for 2 and 3. Okay, so 2 and 3 will be pushed into the stack. So let's make a dry run of the above pseudo code. The code is not complete, there are a few more things you need to do, but let us the basics. So initially the stack is filled with 1. Okay, so you take out 1 since 1 is the last element. So the children of 1 are 2 and 3. Okay, so this is the reference tree we are talking about. Okay, so that one has two children, 2 and 3. So now we push 2 and 3 in the stack. Okay, so we push 2 and 3 in the stack. So now the stack contains 3 and 2. Okay, so again we take the last element of the stack, that is 2. So we take out 2 and push the elements of 2 in the stack. So 2 has again two children, that is 4 and 5. And we will also keep the track of the sequence. So initially 1 was popped out, so we have 1. Now 2 is taken out, so there is 2. Okay, so now the stack contains 3, 4 and 5. Okay, so we will again take out the last element, that is 5, and now the stack, and now since 5 doesn't have any children, so nothing will be pushed into the stack. Okay, so now the stack is like 3 and 4 only. Okay, so our sequence now has 5. Now we will take out 4 since it is the last element. So now our stack has 3. Okay, and we add 4 to the sequence. Similarly, we will now take out 3, and we will push the children of 3 into the stack. So stack has two, 3 has two children, that is 6 and 7. So we add 3 to the sequence. Now we take out 7, and our stack only contains 6, and then we take out 6 and our stack is empty. So we come out of the loop. So our sequence is something like this: 1 2 5 4 3 6. So we started from 1, we went to 2, then we went to 5, then we went to 4 because that's the other children that was not visited. Then we came to 3, then we explored 6 and 7, which are the children of 3. So this is basically the basics of DFS. So if we talk about the basics of BFS, so in BFS we use Q. Okay, so everything is same. Just one thing will change, that here we will take out the we are taking out the last element. Now we will take out the first element in the queue. Okay, so as I told, everything will be the same. Just we will take out the first element. So instead of stack we will use queue, because we need to take out the first element in the uh, array or in the queue. So this will be queue, and it will take out from front. Okay, we will take out from the beginning. Okay, and we will insert from the end. So queue is FIFO, like first in first out, like you come first, then means first come first serve. So you have to enter from the end and it will come out from the beginning. Okay, so it will be inserted at the end, but while taking out it will be taken out from the front. Okay, so again let's take the previous tree only. So initially our queue has the root, that is 1. So we are exploring this tree. So we take out the first element in the queue, that is 1. So now we will insert the children of uh, 1, that are 2 and 3. So we will take out again the first element. So we also maintain the sequence. So we have taken out 1 in the beginning. So now we will take out 2, because 2 is the first element in the queue. So and we will insert the children of 2 in the queue. So now queue has 3 4 and 5. Okay, so again we will take out the first element 3. So our sequence is now 1 2 and 3. So basically our queue now looks like 4 5 6 and 7, because we have inserted the children of 3, that is 6 and 7, in the queue. So now we will take out 4. 4 doesn't have any children, so nothing to insert. So our queue has 5 6 and 7. Then we take out 5. 5 again has nothing to insert, so 6 and 7 are there. We take out 6. So Q only has 7, and then we take out 7. So Q is now empty, and we stop that. So our sequence becomes 1 2 3 4 5 6 7. So here you can see that we have explored all the nodes in a current level. Then only we have gone to the next level. So first we have explored level 0, that is 1. Then we have explored all the nodes of level 1, that is 2 and 3. Then only we have gone to the next level, that is 4 5 6 and 7. Okay, so this is the basic thing for queue. Okay, so BFS is generally used when you are looking for shortest paths. Okay, so here another thing you need to observe, that the nodes which are at a distance of 1. So nodes 2 and 3 are at a distance of 1 from the root node, right? So the nodes which are closer to the root node are visited before than the nodes which are further or more distant from the other nodes. Okay, so for example, 4 is more distant than 3. Okay, so 3 is closer to 1 than 4. So in BFS, 3 will be visited before 4. But in DFS, this was not the case, because you can see that 4 was visited before 3. So in BFS, nodes which are closer to root will always be visited before than the nodes which are distant from the root node. This is one of the most useful properties of BFS. So by this property, you can use BFS to find the shortest paths in a graph or in a tree. Okay, so this is basically an overview of a BFS and DFS. And now trees and graphs are almost similar. Okay, so what is the difference between a tree and a graph? So the only difference between a tree and a graph here is that the number of nodes, if the number of nodes in a tree is n, so let's say there are n nodes in a tree, so there will be exactly one path between a pair of nodes. Okay, so the special property of a tree here is that there is only one path between a pair of nodes. Okay, so if you see this diagram, so let's take any pair of nodes. Let's take 8 and 5. So there is only one path if you want to go from 8 to 5. So the path is like you go from 8 to 4, 4 to 2, and 2 to 5. Okay, so in tree there is only one path. Okay, so there is exactly one path to go between any pair of nodes. But in graph there can be multiple paths. Like, let's say if we add an edge from 8 to 5. Okay, or let's take this example, like this one. Okay, so let's say that we add an edge between 6 and 7. Okay, so now there are two paths for going from 6 to 7. One path is 6 3 7. You can go like this, you go 6 3 7. So you can reach from 6 to 7 in this path. Another path is that you directly go from uh, 6 to 7. So there are two paths. So this is now a graph. Okay, not a tree, because in tree there will be exactly one path between any two pair of nodes. But here between 6 and 7 there are two paths. One path is 6 3 and 7, like you go via the 3 node, or you go directly from 6 to 7. So there are two nodes. This is not following the condition. So this is now a graph. So this is the basic difference between a tree and a graph. Otherwise, all the other terminologies are exactly the same. Every endpoint is called a node. The connection between two nodes is called an edge. Okay, so other terminologies are the same. So basically, these two algorithms are very important for trees and graphs. So now let us talk about weighted graphs and weighted trees. Okay, so it's not very complex. So let's say let's take this tree again. Okay, so there, as you can see, that there is a edge between 2 and 1. Okay, so the edge between 2 and 1 doesn't have any weight or doesn't have any value. Okay, okay, so let's say you want to go from your friend's house to your house. So let's say anyone ask you that what is the distance of the road that connects your friend's house and your house. Okay, so you will say that it is x kilometers. Okay, so let's say you live in house 2 and your friend lives in house 1, and somebody asks you what is the length of the path that connects your house and your friend's house. So let's say you say that it is x kilometers. So let's so the weight of that edge will be x. Okay, so when the edges have an weight or the edges have an value, okay, so then the tree is a weighted tree. Otherwise it's an unweighted tree. When the edges doesn't have any weights, so it's called an unweighted tree. Otherwise, if the edges has an weight or has an value, so they are called weighted tree or weighted graphs. Okay, so now what let you might ask, what's the real life applications of weighted trees? So again, as I told, let's say you live in house 1. and your friend lives in house 7. Okay, so you want to find out the shortest path from your house to your friend's house. So let's say the road that connects your house to this house is of 1 kilometer. Okay, so let's say it's of 1 kilometer. So similarly, the other roads will also have some value, that is the length of their roads. Okay, so in these cases, it's important to have some values, like the roads or the edges must have some values, because if we don't have the length of the road, we can't calculate the shortest path, right? So in these cases, the connections must have some value so that we can find the shortest path. Okay, so this is the thing, like when we means when weighted graphs or trees are being used. Okay, so that's that's covers the basics of the things. Okay, so means that covers the basics of graphs, trees, and the fundamentals of this hierarchical data structures. And if I talk about the interview preparation of like trees and graphs, so like trees and graphs are very important. Like in almost every interview I faced, like there was at least one question of trees and graphs, and like every question revolved around DFS, BFS, and shortest path in a graph. So like these DFS and BFS is very important, and like before you jump into shortest path, you need to master DFS and BFS completely, because shortest path is implemented using BFS. Okay, so what you can do, you can go to lead code and like start practicing about DFS and BFS, because like DFS and BFS is hell important from the point of view of interviews. And like you can start with the easier problems and then gradually go up to medium and hard level problems. So always remember that when you need a LIFO system, you have to use DFS, and when you need a FIFO system, you need to have BFS. Okay, so always remember this, like when you are confused that what should I use, DFS or BFS. So if you need if the algorithm requires that the last element should be processed first, then you go for DFS. And if the algorithm demands that the first element inserted needs to be processed first, then you go for BFS. So this is the basic difference, uh, and this will help you in choosing DFS and BFS for your algorithm. Okay, so I think that's the basic things I wanted to teach in this session about graphs and trees. I don't want to go into very depth for this particular session, because this is a new topic and you need some time to get this into your head. Probably we will have another extra session where we can go more into depth, like Dijkstra, 01 BFS, and shortest path algorithms. So that's I think I that's pretty much about this session. So if you guys have any question, like you can ask in the chat and like I can answer. Otherwise, I think we can end. So I will like wait for like 15, 20 seconds for any questions, and then we can end the session. So I guess nobody has any questions. So I think we can end the session. So see you everyone in the next graph or tree session, like where we can dive more into details like Dijkstra, 01 BFS, and shortest path algorithms, which are very important for interviews. And we will dive into those algorithms and topics in the next session, maybe. So see you guys. Have fun learning DFS and BFS. Like, go and practice problems from lead code. It will help you to understand how the algorithms work, and like it will also help you in understanding the shortest first algorithms we will discuss in next session. So see you guys. Bye.